Okay, thank you, and thanks everyone for coming to the talk. So as the title suggests, today I'm going to talk about intrinsic information, and I'm going to talk about this in the context of integrated information theory. Now, in 15 minutes or so, I of course can barely scratch the surface of IIT, but I'm going to give just a few points to kind of set the stage for why I'm talking about intrinsic information. So for those who are not familiar, this would be very fast, but otherwise, the idea of IIT is it starts from axioms. Axioms are considered to be fundamental truths about consciousness or subjective experience. So we have here this intrinsic existence, I exist for myself. Composition as an axiom basically says that there are parts or aspects of my experience. Here I've got listed, there's book, there's the color blue, there's the left side of the experience. Information as an axiom says that my experience is specific. It is what it is, so to say. And then from that, it is therefore different from the many other possible experiences I could be having. Integration says it's unified, it can't be divided into two separate experiences without losing something. And exclusion is that it's definite. It is neither less, say the same experience without color, nor is it more, say the same experience with a very vivid awareness of my blood pressure. So those are the 5 axioms, sometimes intrinsic existence is split when we say 0 plus 5 for IIT. And then the premise is that if these axioms are cover all of the fundamental properties of consciousness, that is, their kind of necessary and sufficient properties of consciousness, then our goal is to take these phenomenological axioms and translate them into mathematical postulates. And the idea being then the postulates would give us the necessary and sufficient requirements for a physical substrate of consciousness. Hypothetically here, the brain, although a lot of the work is done using kind of these small graphical networks. So that's the premise of integrated information theory. Then the postulates capture everything. And so assuming that we get the axioms right and the translation to the postulates right, then we would have all the mathematical tools we need to understand what the experience is and what it's about and so forth. So one very specific aspect of the translation to postulates is this idea of a mechanism or a part of the experience. So the experience has parts, that's composition, and the translation of that into a postulate is that the system has parts. So if I have this simple system ABC, I can consider a part of the system might be B and C together. They form a mechanism. And this mechanism has causes and effects. That's derives from the existence axiom. To say that to exist, you must both be able to affect something and be affected by something. So this mechanism has causes and effects. And essentially what we want to do is we want to measure the integrated information of a mechanism. So the integrated comes from the integration axiom and the information comes from the information axiom. And so I've got here this ABC idea. So BC is the mechanism. It's the thing which is having an effect, in this case, on A. Hypothetically here, I have A has AND logic, so it only turns on if both B and C are on. And I can look at the probability distribution of A given BC. So if B and C are both on, then A will turn on with probability 1, and otherwise it will turn off. But you only see here conditional on BC being on. And then the integration aspect is that I cut the mechanism. So in this case, I cut away B. And I get what would be called the cut probability distribution. And in this case, that's just probability of A given C. So now I know C, but the link from B has been cut. I consider that essentially unknown. And so now A is equally likely to be on or off, because if B was on, then it would go on, but if B was off, then it would be off. So I have this what I'll call the intact distribution and the cut distribution. So I have two probability distributions, and I want to measure the information, the integrated information. I take the difference between those two distributions. And then there's an aspect where for larger mechanisms, I cut it in all possible ways, and I take the minimum over the different cuts. But here, my main focus is on this function D, which defines the integrated information between an intact probability distribution and a cut probability distribution. So that is my very brief introduction to IIT, and specifically the thing that I'm interested in, which is defining the integrated information of such a mechanism. So where's my talk going to go from here? Well, first I'm going to introduce a measure of intrinsic information. And then once I've introduced it, I'm going to circle back and discuss this measure in the context of IIT. So I'm going to introduce intrinsic information by way of a motivating example. So here's the example. You are sealed inside an enclosure. Your only contact with the outside world is an input channel that displays symbols on a screen. So you can see this screen. And then you have a keyboard that you can use to send messages to the outside world, an output channel. So you see a symbol and you can press the symbol. And essentially your task from inside this enclosure is you want to relay the symbols that show up on the screen through the output channel using the keyboard. It's a fairly simple idea. One of the keys here is that you're kind of sealed inside this enclosure without other access to the outside world. So when I define the intrinsic perspective, I kind of put this box around something. And that's, in this case, the thing whose intrinsic perspective I'm trying to take. So to explore this example, we're going to consider three different enclosures. The first one, which I call the bit enclosure, and it's called that because the input channel is a single wire that carries one bit signal. So it chooses between two possible symbols, let's say a dot or a dash. Dot shows up on the screen, and then you can relay the dot with the keyboard. Say the keyboard also only has two symbols you can press, and it goes through the output channel. The second enclosure, I'm going to call the byte enclosure. So same general idea, but now I have 8 binary wires coming in. So I have 2 to the 8 possible symbols that can be displayed. Say something like ASCII characters, although I don't think that's exactly right, but that's the idea here. So again, you see a symbol, in this case, the letter I, you press the I on the keyboard, and you can output it through another byte-sized channel. And now my third enclosure is what I'm going to call the noisy byte channel. So again, I have 8 wires, just like the byte channel, but now 7 of those wires are noisy. That means whatever signal is sent through them gets scrambled. So you may not be receiving what the sender entailed and expected you to get. There is one of these channels is left still intact. It correctly transmits one of its kind of 8 pairs, but overall it's noisy. And so the question is, which of these enclosures should you choose for your task? Kind of deliberately avoiding phrasing like which one transmit the most information or something like that so far. So my opinion here, my thinking is certainly the byte enclosure, the middle one, is the best of the 3. But why is it better than the other 2? So it's better than the bit enclosure because it has more potential symbols. My repertoire of possible symbols that can be sent to me and can be relayed is larger, so I can potentially transmit more complicated messages. I could convey more details in a single symbol, and that seems like a benefit. And then by contrast, if I look at the noisy byte symbol, now I have the same amount of symbols available to me, but the problem is it's noisy. I'm not necessarily getting the correct symbol from the sender, and so whatever I send to the receiver is often going to be incorrect. I'm not going to be accurately relaying the messages that were given to me. So there's two reasons why I think the byte enclosure is better. It has a larger repertoire of possible symbols, and there is no noise, so it transmits them more accurately. I think that is, for the most part, uncontroversial. But then the follow-up question is, well, what about comparing the bit enclosure to the noisy byte enclosure? Which one of those would be better if, hypothetically, the noiseless byte didn't exist or was taken by some other person in an enclosure? Well, if you use something like Kullback-Leibler divergence or mutual information, one of those kind of standard information measures, what it will tell you is that both of these input channels is able to transmit one bit of information. Here I get my dot or my dash, and here I get 1 out of my 8 bits being correctly transmitted. So from a KLD perspective, you might conclude that they are equally good. They're equally good at transmitting information for the job that you can assign. But my claim is that from the intrinsic perspective, the bit channel is better because it is transmitting more correct signal. And so I want to break that down a little bit. So first on the more correct signal part. So the bit channel, every symbol transmitted is correct. So if, for example, in 8 transmissions, I will transmit 8 correct bits, or a byte, I will, you could aggregate that, somebody on the outside of the enclosure could aggregate that into one correct byte-sized character. On the other hand, if I look at the noisy byte channel, then only 1 out of every 2 to the 7 transmissions is going to end up showing me the correct symbol. And so I'm only going to transmit a correct symbol on average every 128 or 127 symbols transmitted. So I get a byte-sized character from this enclosure every 8 transmissions, and a correct byte-sized character here every 128 transmissions. So from that perspective of relaying the information, I'm doing a much better job using the bit enclosure. A few more things we could say about this is, well, why does the KLD assign 1 bit of information to this enclosure when it's never really transmitting the correct signal or symbol? And the idea here is, while I don't get the right symbol, I do learn something, right? I can take my alphabet of 256 symbols, and if I know that this bit is always correct, I can basically take my 256 possible and reduce that to 128 possible symbols. I have essentially eliminated half of the potential symbols from consideration. I've learned which half of my symbol I'm on. And if I wasn't kind of constrained to be in this box without communicating with the outside world, I could implement a naive error correction code by saying, okay, well, let's take my alphabet, which has 256 symbols, and let's take these first 128 and map them to dot, and the second 128 map them to dash, and now I can accurately transmit dot or dash every time because I'm able to constrain to 1/2 of the symbol set. And so by communicating an alternative method of communication, a new alphabet, I'm able to recover the noiseless bit from within the byte channel. And in essence, I can take my noisy signal and I can separate the signal from the noise and recover that 1 bit of signal that was in there and discard the 7 bits of noise. And then the claim is that, well, from the intrinsic perspective, you can't do that. And what I mean by that is whose intrinsic perspective am I taking here? Not me, the scientist or the mathematician who's computing probabilities and measuring things, but to the person in the enclosure or to the enclosure itself. Its job is to relay symbols. And so for it, it can only do what it was designed to do. So one more way, and I just want to kind of circle around here and say, well, it might seem like this this enclosure who can't change its alphabet and who can't communicate with the outside world is kind of contrived. But imagine instead of an enclosure, it's a neuron. And the neuron simply receives, simplistically receives spikes at its dendrites, and then in a very mechanistic fashion, processes the neurotransmitters, and then it either spikes or it doesn't spike. And the neuron doesn't know the channel. It can't change its alphabet. It's a neuron. It has its mechanistic function it does, and that's all it does. So I think if you consider a neuron, which is, of course, if we're studying consciousness, where we want to go with this, it makes a little bit more sense to say how the neuron can't go around and separate the signal from its noise. It gets whatever spikes it gets, and then it has no choice about what it does with them. It simply converts them into an action potential or not. So based on this, we propose 3 properties for intrinsic information. The first one is that it's kind of trivial, that it's 0 if and only if the signal makes no difference to the symbol received. Basically, if the 2 distributions are the same, it must be 0. The second one, intrinsicality. This is based on my arguments from the byte and why the byte was better than the other 2. It says if we have a larger alphabet, intrinsic information should increase. But if we have more noise, it should decrease. And lastly, specificity is that it should be based on a specific symbol. Basically, the symbol that was received from the screen, or what the person in the enclosure or the neuron must use to make its decision whether to fire or not, or what key to press. I'm going to, it's a mathematical conference, so a little bit of a result here. So if we define the 2 distributions of interest, P to be kind of the conditional probability and Q to be the marginal probability, and I'm going to have some special notation for things that are what I call fully selective. That means that something occurs with probability 1, and fully noisy, which means everything's equally likely. We can take those 3 conditions and make them more precise. So for a distribution with n possible symbols, the difference between them is 0 if and only if they're equivalent. Expansion, that means if I expand my alphabet with this without incurring any more noise, so I do that by having everything fully selective, then I get additivity in my intrinsic information. And dilution, which means if I expand my alphabet with no more signal, just purely with noise, then I necessarily decrease by, say, a factor of 1/m, where that's the number of symbols I increased by. And then specificity, which means I should be the maximum of some symbol-specific information function evaluated over all possible states. I have these properties, and then we have this paper, it's in Scientific Reports, which shows that for a function d which satisfies these properties, and there are some regularity conditions involving smoothness, then the unique solution is that the intrinsic information, we call it the intrinsic difference, is the max of f p q, where f is k p log p over q for some positive k. Okay, and I think, so that's the main result. I just want to get to one more point. So here we go back to our motivating example. KLD gives the same answer for both, whereas the intrinsic information goes down as we would expect due to the noise. And then why is this important for integrated information theory? Well, integrated information theory has used multiple different difference measures to measure the difference between probabilities over its lifetime, starting with the KLD and then to the Earth mover's distance. And what's important here is that if we now switch to the intrinsic difference for evaluating mechanism integrated information, it's unique. So now consciousness is the way it is, so it can't be subject to this degree of freedom on the distance measure. It has to be, there has to be one correct one. So the uniqueness is a strong result there. And more importantly, it's motivated by the axioms and postulates. So the original KLD was just kind of taken as the default of what any person would start with. There was some reasons why the Earth mover's distance was used, which have since kind of become obsolete with some of the new developments of the theory. And so now we've got this measure, which is motivated by intrinsicality and by information and causality. And it kind of helps move the theory towards a unique cause-effect structure, unique solution. I did have this one example, but I think I don't have time for it. So I'll end here with just a summary that intrinsic difference is a unique function that satisfies our 3 desired properties. And this uniqueness is an important result for the development of IIT.